What? No, who's that? What I was just singing? Huh? What I was just singing? Yeah. Wait. No, no, 21 questions. No, it's not the same.
It's not what?
No. I'll give you a hint. Friend of Snoop Dogg's in that whole crew when they were coming up.
Oh,
No.
no. What? Fuck.
He was not really like, he didn't do that much stuff on his own, but he did a lot of background vocals for people. And,
Oh.
yeah.
That's right. Did you want that guy? Listen to me.
No, that's still Dr. Dre.
The singer.
Wait, like it's Nate Dogg.
Yeah.
Nate Dogg. Like you said it.
Yeah, he's that part. Just that part.
Oh,
Okay.
I'm listening to the sad girl sing about
We should go push your hips back behind you and push your rib cage towards that wall. Soft knees. You're going to soft knees. Make your back more flat. You're pushing it hard with your butt. Really relax. How's that? You feel the stretch all the way down? Yeah. So that's something you can do. Just like foam rolling out that area. Make a difference in this. But we always do the right hand side. It's all position. Our right core is stronger than our left.
Depending on which hand you're dominant with?
Not even, just because of the way that we breathe. Like the liver's on the right hand side, and we've got 3 lobes of the lung over here, there's 2 on the left, so we've got marking on this side. And it just so happens that we get more air on the left hand side and less air on the right hand side. And so it puts your rib cage in a better position to contract your abs on the right. So it just pulls everything down more to the left. So like if anything you want to work on, kind of being able to drop the right side and then do like side, like left obliques are better than right obliques basically.
Really?
Otherwise you're gonna be like, a lot of times people balance more on the left side leg than they do the right leg, even though they're right-handed, because the right abs are stronger. So like your contralateral core will keep you balanced. Where like you get somebody on the right leg and they're gonna be like all wobbly because their left abs are long. So, but for you, just like formulating on that flat is really, really painful. And then just trying to stretch it out. No difference in the short term. If it doesn't really fix itself, there's other things you can work on surgery. It's interesting. It's That's all it is. Black holes. Push it over with your butt, head down, or a little bit more. It works really well in like a doorway. I usually grab it like a doorway. That's probably you should feel a stretch like from right underneath your arm all the way down the side of your back to like your low back. Yeah, it's a pretty big one. Yeah, right side should be tighter. So like your right shoulder blade is more down as you rotate it. Your left shoulder blade, when you aim the arm or you lift your arm out to the side, about 30 degrees, that shoulder blade should start to move.
That's just a try.
And that just means that on the right hand side is good. It'll start earlier and it won't go as far. It's like earlier. But if you were to do like a new overhead elevation, like for me, like if I'm keep everything stable and reach overhead, my right arm goes more time. I have to work harder, like natural range of motion. I have to do my back to get my arm to go up to a 30. It should be the same thing. It could, yeah. I mean, it could, yeah. There's also like you gotta be careful with it because you don't necessarily want to stretch yourself to the point where like just like stretching yourself to the point where you don't like motion is always good. Like to get to a natural range of motion is okay, but there's other things. A lot of times it's just nervous system. Honestly, so like a lot of people think their hamstrings are tight. It's not that their hamstrings are tight; they're actually pretty long. It's just that their nervous system, like your brain's telling your hamstrings all the time, like I need to be tighter or I'll fall over because they're basically helping to fight gravity. Right? But if you take gravity out of the equation and get them to almost shut their nervous system down in that area, their hamstrings are like. So you see that a lot like hospitals. They'll like get on band and they'll like stretch the ground and everything, right? And at that point, all they're doing is loosening up their joints. They're just stretching out the tendons and ligaments around the joints, which is fine if you have muscle. But when you don't have muscle, like what's going to happen to that capsule? I don't know. It's not a good idea. But usually like it's totally fine to stretch out. And it just gets really tight throughout the day. We use it as a posture muscle. So if that's short, tight,
all right. I think I'm about ready to get started. Wow, we skipped the day. It feels like a long time ago, but not really. So there is homework due on Saturday. If you have, so you're not late, but if you happen to have it now and want to hand it in, okay, so as some people already have, that's fine. And you have to take it off your hand, and then you don't have to worry about electronically getting the paper homework to you, okay? If you are still working on it, which is totally fine, or you go, oh damn, I left it at home, then just email it to me in a reasonable way. A PDF is fine, a JPEG is fine. Most photo-like formats should be okay. If you, just so we know how this is going to work, okay, if you decide you want to email it to me, I will email you back within 24 hours, okay, so sometime on Sunday, and you'll have one of two things, okay? It will either be a grade, or it will be an I can't read this, okay? If it's an I can't read this, then we'll try and figure out why, okay? Try to make sure it's not blurry, okay, or something like that. You should be able to look at it, and you should be able to fix those, okay? Anybody have a problem getting to something other than JPEG or PDF? Can you do those? Okay. Anyway, you'll either get back a grade or you'll get back a I can't read this. If you get back an I can't read this, then we need to try again. Okay? And we need to come up with so I would on Sunday send you something. I would expect that by Monday you would have a second attempt. okay? So don't throw out your stuff after you shoot your JPEG picture just in case I go, yeah, this did not work. Okay? Good. Probably will. Good? Questions about that? Yeah.
Can you help us out with one of the things?
Can I help you out with some of them?
Yeah, we had a question on one of them, and I was wondering if you could kind of walk us through it and help us understand.
So here's, I have no problem with doing that, okay? What I do have a problem with is doing that as a main focus of class, okay? And so what I would like to do is move on with the stuff I was going to do now, and then we're going to do another in-class problem, and you might finish early, okay? Or even if you don't finish early, I don't mind staying, you know, a few minutes afterwards to talk about something. Okay? Cool. We'll see. Today, I'm going to be talking about waves and that sort of stuff. We'll be doing a problem. We might have a half hour at the end that we could talk about homework and that sort of thing. Okay? Good. Any other homework-related questions? I did post assignment 2 and assignment 3, so you should be able to see those now. Did people see them? Yes, good. Okay, making sure that it really did work. Good. Okay. And I think those are due Tuesday evening and Monday evening. So, and then we have an exam a week from this Tuesday. Good. Okay. We also. I realized I was going to bring in the appendix for the 114 lab manual to talk about how to handle uncertainty and that sort of thing. And I realized as I was writing in this afternoon that I had not done that. So I made myself a better note. Okay, I actually did all the things that I made notes of, but I forgot to make a note of that before. And I will post that on Canvas. Okay? But I'll talk to you a bit about the types of this is the analysis in the formal lab and what I'll be expecting, and then you can know that sometime tomorrow, hopefully early afternoon, I'll have that posted on Canvas so you can refer to it. There are in the back part of the lab manual, it talks about 5 things that your lab should address, okay? One of them is that you should experimentally determine K for your spring. It turns out there's a way that's pretty good to do that, okay? And a way that's pretty good to look at a lot of data like this. You collected some data that was delta X versus the mass that was hanging on the spring, right? Okay? And you changed the mass to a bunch of different values, and then you measured what this delta X was. This has plus or minus so many millimeters, okay, or centimeters or meters or something. You've got some uncertainty there. This is plus or minus so many grams. That might have been, should have been pretty easy to estimate. You had a meter stick or something like that that you were using to make the measurement. It probably went down to millimeters. And then, depending on what it was you were looking at, it may have been easy to measure within a millimeter or harder, okay? But definitely attempt to quantify that. This one, you had different masses. They were labeled probably to within a gram. They might have been accurate to within a gram. You might have measured them on the scale over there, which can get down to 1/10 of a gram. 100th of a gram? Maybe 1/10 of a gram? I think it's 10th anyway. And that would have been better, okay, just because some of these things aren't exact. Also, if you put a bunch of tape on or something like that, that could be a gram or 2. So anyway, that should go into your estimate of what the uncertainty in that is. Then, what you can do is make a graph, okay? And that graph, perhaps you say, here's my mass, and here is delta x, and that graph should, if you add more mass, delta x gets bigger, and this should be a line, okay? You can plot your graph with error bars, okay, indicating the uncertainty in, say, the delta x. Now, I may have drawn those a little bigger, but a full page. Okay. Then, and there is a method in the appendix of the lab manual that talks about how to compute the slope. And the uncertainty in the slope. Okay. Why would we care about the slope?
That's
It's not k here, but it's very related to k. Okay. Basically, the slope of that would give you the spring constant. If this were force, okay, if this were in newtons and this were in, let's see, if we did it like this, if it was in newtons per meter delta x, if you plot it like that, then this slope is k, okay? If you plot mass here, then the slope is not k, but it's related to k because the mass determined how many newtons there was, okay? So, so you might, the right thing to do is convert that into newtons, and then the slope would be k. Okay? If not, then you can use delta x is equal to it would be, or I'm sorry. You could use the weight that you placed on the spring is equal to k delta x. Okay, that weight would be mg is equal to k delta x. And then you could see that if you plotted m here, the slope would be k over g delta x. This is still a constant that you could measure. And then if you took that measured slope, if this were m, and you had k over g was your slope, if you took the slope of that and divided by g, you'd get k. Okay? Now there was a question back here? Maybe? Still there? Yeah.
Does it matter which way we use to figure out k?
I don't care as long as what you're going to want to do is use the slope to figure out k, and I want you to use it correctly.
Okay.
So if you do newtons here and say, this is my slope, that's fine. If you do mass here and say my slope is k, that's wrong, right? Because it's really related to something else. If you switch these around and then handle it correctly, I'm good. So if you've already done the graph and you're saying, I don't want to redo my graph, but I can totally get k from it, that's fine too. Does that make sense? So the important parts, use the graph, use the slope to get k, estimate the uncertainty, estimate the slope and the uncertainty in the slope, and do it in one of the many correct ways. Good? Okay. There are also many not correct ways too, so don't avoid those. Good? Okay, so this should give you, in this, you should have the spring constant for your spring and the uncertainty in it. Okay? The next thing that you were measuring was, you were relating, was period is equal to the square root of k over m. I'm trying to do too much math or that. Period is 1 over the frequency, which is equal to 1 over And this formula predicts a relationship, right? It predicts that if you do k, as you now do, and you know 2 pi, if you plugged in a math, you can find the period. If you collected t versus m data, okay? So, just like over here, you could make a plot, okay? Now, you wouldn't expect m and t to be related linearly because of that square root, okay? But if you square both sides, you end up with t squared is equal to 1 over 2 pi squared m over k, okay? So, if you were to make this sort of graph, if you were to say, here's my mass, here's period squared, okay, you would expect to get some sort of line, okay? You'd have data points that are distributed around it, and then you can estimate the slope and the uncertainty in the slope. What would you expect the slope of this to be? What's the formula for a line? If you were doing algebra. Wait. Y equals mx plus b. Yeah. Okay. So we often learn that for an equation for a line. Okay. And the picture would look something like this. We'd say y is on this axis, x is on this axis. Here, this is the slope is m, and b is the intercept. Okay. Now, so you want to sort of generalize this. You want to say, well, y is the thing on my vertical axis. X is the thing on my horizontal axis. It varies. M is a constant, okay, and b is some constant that I'm adding to it, okay. If our formula is this, t squared is equal to m over 2 pi squared k, okay? And we plot this graph, what's on the vertical axis?
Just t is 2 pi squared instead of 1 over 2 pi?
T is 2 pi squared? Yeah, what? This is right, isn't it? And isn't that right? No. You're right. Sorry. My 2 pi should be up here. Because omega is 2 pi f. This is what I. So. Yes. So you're right. Good? Better? Okay. Now, if we plot this, if we plot t squared versus m, t squared is on our vertical axis. Okay? So this t squared is also, we've written it out in the form where the thing on the vertical axis is what is equal to the other thing. Right? The other thing has our variable. Okay, this is m instead of x, so m is the thing on the horizontal axis, and then it has some constants. Okay, so this here is the slope. Yeah? Okay, because that's the constant that you're multiplying by. This constant times m gives you t squared. That makes the form like mx plus b is equal to y. Yeah? Good? Okay. So if you make this graph and you measure the slope, okay, it should match this. So you can measure that slope and you can get a number. Okay? And you'll say, this is 5 plus or minus 2. And then you can say, well, what I would have predicted is 2 pi over k, this is what I had for k, does 2 pi over k match what you got for the slope? Okay? And it has some uncertainty. If they overlap, if you've got like 5 plus or minus 2 and 4.5 plus or minus 1, you go, oh yeah, those agree pretty well, right? Because, 5 plus or minus 2 incorporates 4.5, they overlap. If you get, this slope is 10 plus or minus 1, and when you calculate 2 pi squared over k, you get 3 plus or minus 2, then you can say these disagree, right? Because 3 plus or minus 2 doesn't match, doesn't overlap with 10 plus or minus 1. Yeah? Okay. So that's how you can compare the quality of your results. Okay, in your conclusion, you say, this is what we measured, and that's what we got. The other thing you're going to be doing is make a prediction of what the motion looks like. Right? So you can, we said it, you display in the third part, you displace the spring by 15 centimeters, it oscillates back and forth, and you know the spring constant K, you know the mass that you put on the spring, you know the formula, you know that X is equal to A cosine omega t, okay, which is equal to A cosine square root of K over M times T, okay, should give you this graph, and you can figure out what that is because you've measured K, and you've got an experimental measurement of K and M, and this amplitude is 15 centimeters, and you can use your calculator and predict what this should look like as a function of T. And then you can compare it to the one that you measured. Yeah? You can do that not only with the position, but also with the velocity and the acceleration. Seem okay? Okay. So I will post by tomorrow afternoon the instructions for how to do this slope and uncertainty of the slope. Okay? But this should give you an idea of what to do with the data in your lab. Yeah? I think I also posted on Canvas that the formal lab is due next Saturday, which is what we discussed in class. And feel free to hand in a draft sometime next week.
Week from Saturday, right?
A week from Saturday?
Yes.
It's a week?
Well, you said next Saturday.
Yeah, next Saturday.
So a week
Yeah.
from Saturday.
Yeah, July 9th. Not 2 days from now. Okay?
Okay, yes.
But yeah, that's right. That's right. Okay. Second. It's not this Saturday. It's next one. Okay. But the one at that one, the 9th. Yeah. Okay.
Yeah.
Good.
I'm not confident.
So
I already did this problem.
it's time for us to discuss some new phenomena. Our new phenomenon is related to oscillating motion, but it's not the same thing. Okay? It's what we're going to talk about
Dude, I'm not gonna.
is waves.
I totally could.
Okay? And so we've got a number of different examples,
I was gonna.
but the first thing I want to talk about is the
What?
If you need more
is-
time, just do it.
just sort of like what we did with simple harmonic motion. We talked about what is oscillating motion, and then we talked about things like amplitude and period, frequency, and we started to label these things that describe the motion. With wave motion, we have some similar stuff that we need to talk about. Okay. One of the examples of wave motion is a stretched spring, okay, or a spring will do this. And if you stretch something like this, and you do something like pluck it, okay, I disturb it a little bit over here and let it go, okay, you can see a pulse move down the spring, okay, if you notice, it took off this way, okay? It hit the other end and then it bounced, okay? But if you imagine a very, very long string, it wouldn't have bounced. It would have kept on going, right? It was just moving along, okay? So, we can, well, there's some things to notice about the spring, okay? First of all, what's moving? What's moving? The spring. How is the spring moving? Up and down. Yeah.
It's like a wave.
How's the wave moving? Which way does the spring go? The spring goes up and down. Which way does the wave go?
The same.
Does it go up and down too?
It just kind of carries throughout the amount of force that you put in.
What?
It just kind of carries that same shape like all the way to either side, and then it'll.
Yeah. So there's this shape that moves along the spring, right? So I'm plucking it like this. So I've got this end is up and that end is down, and I'm going to let. But you saw that shape propagate across the spring, right?
Yeah.
Did the spring propagate across the spring? Did this coil go that way?
Yeah.
Huh? It did?
No.
I mean, maybe a little bit. It might have wiggled a little bit this way, but it's not like this coil is going all the way down like that, right? It's not like the spring is going that way. What's happening is the pulse is going that way, right? And this is a different kind of motion than we've talked about before. Typically, when we said something, if I go, how is this tape moving? You know, and I go, do that, the tape goes with it, right? Okay? But here, I shake the spring and the pulse goes that way, but the spring does not. Yeah? Okay? So that's a typical thing about waves, is that the actual material wiggles, okay? But it in itself doesn't move, okay? What sort of things make this pattern, wave-type patterns? We got this spring. What else does that? Water? Okay. So I have a little water tank over here. You want to come look?
Do I ever?
Of course you do. Of course you do.
Here.
Yeah. So it's rippling right now just because it's shaking, but I can do something like take my finger and stick it in here, and when I do, do you see a pulse leave my finger? Okay. Now the water itself doesn't go with it, right? There's a disturbance in the water, right? And that moves as a wave, okay? But it doesn't. But the water itself isn't going. There's also something different about this than that. What is the shape of those waves? Circular, okay? And they do what? How do they travel? Yeah, radially outwards. They get bigger and bigger and bigger. It's not a circle that's moving across this way, but an expanding circle from where I pop my finger in. Okay? It still hits the edges and bounces off, just like it does with the edges over there. Okay? So we'd say this is a two-dimensional wave. Okay? It exists on the surface of the water, okay, and it spreads out. Okay? This is a one-dimensional wave. Okay, it moves along the spring and it just stays on the spring. Are there three-dimensional waves? Sound. Yeah. So how does sound work? We disturb the air. And?
Frequency through the air.
Okay. Yeah. Okay. So just like we did here, we disturb the air. There is a pulse, okay, that it expands, and the pulse can, if I talk, and there are sound waves being created by my mouth and larynx and all, I don't know, I'm not a biology person, but somewhere in there, okay, then they leave and they spread out in all directions, okay? All of you can hear this two-dimensionally around the room, okay? But if you lay down on the floor or, get up in the ceiling, you can hear it as well, right? So it spreads all the way around that way, not just in a plane or in a direction. Okay. Cool. So waves can be one-dimensional, two-dimensional, or three-dimensional. They involve a disturbance, okay? When you disturb, I can disturb this piece of tape, right? I disturbed it, and it doesn't, and it actually moved, right? I disturbed the water, and the ripple moves, but the water doesn't move. The water comes back. When I disturb that spring, the spring moves, wiggles, but it doesn't, the spring material doesn't move down the wave. It comes back. Why does it come back? The air does that too. If I start talking, it's not like you feel a wind coming, a wind coming off, and blowing away. You just hear the sound waves, but the air is wiggled but relatively still, right? Why does it come back? Why doesn't it stay where it was?
It's a surface it can't break through. It's a surface that it can't push through. And it has to.
It hits something it can't. So, definitely when it hits a boundary, okay, like that pole over there, okay, the disturbance can't go through that. Why, when I disturb the spring, when I wiggle this, why does the spring, why don't these coils just go down that way? Okay, or why don't they keep going up? Why do they come back?
I think it's Monday.
Yeah?
They keep coming back because the leftover energy used is transferred somewhere else before it bounces back. I mean, it just bounced back because you have a wall that just...
No,
Well, if you apply force to the spring, it went through the spring, right? And then it needs something that bounced back off of because it couldn't absorb it again.
Alright, let's get rid of the wall.
Ooh, a bigger one.
Okay, so I got a slinky. Okay? And the cool thing about the slinky is that I can throw this out on the ground and there's no wall on the other end. Right? Can I send waves on this without the wall? Oh, yeah.
I'd say you could, it wouldn't come back. But I wanted to say,
Yeah.
can't we consider like the shape of the material that we're working with and the material that we're working with also as having like those type of properties that...
Definitely the material has properties. Are you talking about the shape like...
Yeah, like if that was just a string and you flicked it, you would see maybe like a small wave shoot one direction and maybe come back slightly, but it's not going to retain that amount of force because of the shape that it's lacking. Like that, because it has a spiral shape, it holds like tension a little bit better, right? So, I mean, maybe not tension isn't the right word, but...
No, tension is the right word, but I think actually it has less tension than spring.
Yeah.
Because, you don't have to stretch this very hard, but the tension on this is pretty weak, right? If I stretch a spring, and, if I pull this, a centimeter apart, I can do this easily with my hands, okay?
Yeah.
But I can't do that with a piece of cotton string, right? Because it's too tight. And so I think with a piece of string, the tension would be greater.
Yeah, I guess elasticity is like the word I'm looking for.
Oh, okay. Yeah,
Yeah.
this is actually, well, this is,
Maybe, yeah.
it bends easily and comes back. So with a little bit of tension, you can stretch it.
Yeah.
Okay? It's a stretchy material.
Yeah. Malleable.
Okay? Is it deforming? Am I when I do this, do I break the spring? No, it comes back to where it was before. Oh yeah. So if I take the spring and I lift it up, what do I feel with my thumb here on my left hand? a normal, I feel at least a force by the spring, which way is the spring pushing? Down. So if I lift the spring up, the spring gets pushed back down. Okay? So if I lift the spring, what if I, instead of lifting the spring, what if I push the spring that way? What if I say I'm going to stretch it like this? Well, then my finger over here feels the spring pulling back. So when I disturb the spring from equilibrium, wherever it was sitting, it gets pulled back towards where it was. That's kind of like simple harmonic motion. Yeah? Okay? And actually that is why, in all of the cases that we just talked about, when I disturb the medium where the wave is, the medium pushes back. Okay? So if I lift the spring like this, the spring gets pulled back this way. Okay? And so the spring doesn't keep going that way. The spring doesn't go that way. It just goes back to where it was. Okay? If I stretch it this way, it gets pulled back this way, and I send a disturbance down the line, but I don't send the actual spring. Right? When I was messing with the water over here, okay, and I stick my finger in it, I make like a little hole in the water, okay, and the water is pushing back on my finger. When I lift up, the water comes back in, okay. So I move it away, it comes back. Sound is a little harder to visualize, okay, but you've worked with maybe an air pump or something, and you compress air, you squish it down, and it pushes back on you. Right? Or if you pull the other way and create a partial vacuum, it pushes back the other way. Okay? If the air is a certain pressure, and if I squish it or stretch it, okay, then it goes back to where it was. Okay? And so the sound wave, the water wave, the string or spring wave, they both would do the same thing, depend upon what require that they get pushed back to where they were, okay? And it does depend upon the material, okay, as to how fast it would go. I don't have a liquid other than water. I do have another spring. Well, actually, before I take this off, there's something I want to try. Okay?
That's my first start.
We're not really going to measure how fast it is, but let's just watch this a couple times and get an idea of how fast it is. Okay? If I pluck this spring and send a pulse across,
It's so cool.
there's the speed, right? Okay? It goes about that fast. What if I make the spring tighter? What if I change the tension? Faster or slower?
It's gonna move faster. It's gonna go faster.
So I'm going to change this by doing this.
Organic rock stars.
Okay, it's tighter. Faster or slower?
Faster.
Faster? Faster? Yeah. Okay, so it turns out that the tighter I pull the string, okay, or spring, the faster it will go. The bigger that restoring force is, the faster it will come back to its position, and when it changes things nearby, it goes faster. I can, but you can imagine sending waves down this meter stick, right? You could imagine,
But it'll have to stop at some point.
no, taking it and seeing the pulse go down that way. It,
That's the thing. I think.
when you go, all right, this meter stick is 2 meters long, so it's, and that, it's probably more like 8 meters. So this is about a quarter of that distance, okay? If I plug this in and the wave propagates down there, it goes very fast. Okay? It's a different material, okay? Different tension, okay? The tension in this is incredibly huge. Well, actually, when I plug it like this, the tension isn't that big because this is kind of floppy, okay? But if I were to do this and plug it this way so that my disturbance this doesn't bend very much this way, okay? And so it's going to travel really, really fast, okay? I can send waves down these rods by dropping. If I drop them, I make a disturbance on the other end, okay? And what are you hearing?
Sound impact.
Okay, you hear actually, does it sound sort of like a ring? Yeah? What you're hearing is I disturb this end of this rod. There's a vibration that goes through the aluminum up to the top here, turns around and goes back, and the whole thing starts ringing like a bell. Okay? It does at, well, the speed at which it goes through this, okay, is very high. It'd be like the speed of sound through aluminum. Okay?
Like a guitar string or whatever.
Well, a guitar string is plucked
It would be more like
differently,
that, but
okay? But yeah, so
Same concept.
we should talk a bit about that.
Strings.
Okay.
Strings are cool.
Um,
Strings, you know.
Sometimes your wave is because your wave is traveling in a particular direction. Okay, on this spring, the waves travel this way. If I pluck it perpendicular to the way things travel, what we'll do with that, that's called a transverse wave. Okay, so that's transverse. It's across, transverse, across the direction that it's traveling. Okay, the other type of wave that we that's also a transverse wave, okay? So that there are many ways I can pluck it perpendicular. It doesn't have to be vertical. It could have been horizontal. It just can't be in the direction of travel. If it's in the direction of travel, that's called a longitudinal wave, okay? And it turns out this spring can do both, okay? If I bunch it up like this and let go, there's a little bit of a transverse thing going on, but could you see a longitudinal pulse, okay, that goes down that way? You can see them with slinkies too. Can we run this down the middle of the room? Somebody want to grab the other end?
Ryan. With your organic rock stuff.
You got it? Okay. Why don't you, only some of us can see it. Go ahead and set it down on the ground. Okay? So I can send a longitudinal wave on the slinky wave.
It'll be really
Okay.
hot.
Yeah?
And
Do
then
they-
it's gonna go-
Can you separate them, or are they
Yeah.
racked? Hopefully it's not racked. Cool. Yeah. So we can do a transverse now. Okay, transverse wave like before, okay? Or I can do that and you can do a longitudinal wave. right? Okay, so those are both kinds of waves. You can see it better on the slinky. It goes slower. Tension's even less. Notice those are slow-moving waves compared to these, right? Okay, because again, the tension is less. Yeah?
Yeah.
Cool.
He's flying.
Oh, yeah. Go ahead and your
Okay.
hand is
10.
10?
Yeah.
Here, I will hold it, I will let go. Go ahead and shake it. See, they travel even if there's not a boundary at the other end, right? All they need is more spring on the other end, right? Yeah. Good? Cool.
Hell yeah, Tina.
Good job.
Yeah, good job.
It was on video.
Yeah. You're the fucking superstar.
So make sure you send a release at the end of class.
And I want your autograph.
You also need your social security.
Name and address.
Debit card. For no reason.
So we can deposit direct deposit.
And direct withdrawal. And your savings, say goodbye to that.
You won't need it.
Yeah. In fact, you still owe us money.
Oh,
It's worse. And more profound. And we're now moving into your house. And we're now celebrating Mother's Day with your mom. It just gets worse.
Okay.
And we've already bought you a casket with a graveyard.
So, I want to talk a little bit more about the dynamics of the speed at which the wave travels. Okay. Certainly, we did see it move with it was traveling from one end to the other. We saw that the tension changed the speed. If we increased the tension, it increased the speed. The other thing that can affect it, and we were sort of getting at that, is the material that it's made of, and in particular, how massive it is. Okay? Things that are very massive are more difficult to move. They're more difficult to shake. Things that are less massive, okay, are easier to shake. Okay? So, if this was same tension, okay, but a lighter weight spring, okay, you would expect it to go faster, right? Okay? And if it was a heavier thing, okay, you would expect it to go slower. Yeah? Because the same force isn't going to shake it as easily, right? Okay? So what we end up with is that the velocity of the wave is equal to the square root of the tension divided by mu, okay, which is the mass density of the spring. Okay, so mu is equal to the total mass over the total length. Okay, right. So, and you don't, it's written like this, but really, if you had a section of the spring and you said, what is the mass of this? Okay, divided by the length, that would be its mass density, the number of kilograms per meter. Okay, and it turns out that, even if you said this is an infinitely long spring, okay, it could still have a mass density, right? It would, maybe it's, half a kilogram per meter, but it just goes on forever and ever and ever. Okay, then you could predict what the speed is of those waves. Okay, good. We will do a lab
Tuesday.
Yes, we will do a lab on Tuesday which I think is waves on a string, where we'll be adjusting the tension, we'll be measuring this mass density and verifying that. I think we also do a lab on Thursday, speed of sound. Okay.
Ooh, cool.
So,
Right.
yeah. Okay.
Right.
Good. I've talked for an hour. Let's take a break. Okay.
Yeah.
Let's take.
Throw a frisbee with me.